Continuing on, you have. All right. So if all right, so if P1, which is a particular polar coordinate with the respective r and theta, and P2 is a different polar coordinate, hence why it's r2 and theta 2, 2 points. The distance between them is this following formula. Now, this formula should not look unfamiliar to you all. We actually have seen this formula in some shape, way, and form. I mean, honestly, it's like a splitting image of another formula that we have done this semester, which means it will be on your final. What formula am I referring to? Huh? No, not magnitude. I mean, it did have a square root in it, so I mean, that's good thinking. What other formulas have we talked about this semester that dealt with a square root? Say again? It was used to find the side of a triangle. What was the name of that formula to find a side of a triangle? No, not the Pythagorean theorem, but it did deal with finding the side of a triangle. Say again? Is the law of cosines. Remember, the law of cosines was used to find a missing side of a triangle. It was the square root of a squared plus b squared minus 2ab cosine c. Like literally, it's like the splitting image of it. Okay? But the difference is here is that yes, we are dealing with like angles here inside of a coordinate plane, specifically a polar coordinate plane, and so that's why it's just altered just a little differently. Okay? So in this example, just make sure you know these formulas for your final. Okay? An air traffic controller is tracking two planes that are flying at the same altitude. The coordinates of the planes are at A, as you see, and B, as you see. And of course, their distance is measured in miles. If regulations prohibit airplanes from passing within 3 miles of each other, are these planes in violation? So let's kind of go back to make sure we understand what the question is asking. We have two planes flying at the same altitude. They are at those respective coordinates. Regulation says prohibits planes from passing within 3 miles of each other. Okay? So that means if they're within 3 miles, that they're in violation. So we're trying to figure out, are these planes in violation? If I want to do a quick kind of little sketch of what this could possibly look like, what quadrant would A be? First, second, third, or fourth? Fourth. How many rings over? 5. 2, 3, 4, 5. So right here would be A. Okay? And it has a length of 5 units, and of course an angle of 310. B would be located in what quadrant? 4. How many rings over? 6. And it would be of course, 345 degrees from the polar axis, that horizontal axis. This has a length of 6. And if you recall back from the days of law of sines and law of cosines, when do we use the law of cosines? What particular situation did it need to be to use law of cosines? It was side angle side, okay? And the thing is that if you know that this angle here is 310, and then this angle here is 345, what's the angle in between? 35 degrees. You basically have side angle side. Law of cosines, okay? You got law of cosines right there. That's where that formula is derived from. It's not something they just put a whole bunch of letters and numbers together and symbols. It has a purpose. So to figure out if these planes are in violation, you need to figure out the distance between them. If it's less than 3, they are. If it's bigger than 3, they're okay. So use these numbers, use the formula, find their distance. Do that now. So you plug it into the formula, what you guys get? 3.44 miles. Are they in violation? If it's within 3 miles, so that means if they're within 3, then they are in violation. Okay? So that's how you can use polar coordinates to determine like real life scenarios. Okay, because pilots do use pilots and people at traffic control, they do use polar coordinates here. Okay? So questions before we get to the more involved equations with polar equations. Yes. So that 35 degrees basically represents the angle in between the two polar coordinates for A and B. So if one angle, and I know it's kind of hard to see because of course I use purple, so yeah. So this is 310 right here, so 310. And then the other angle, maybe using black might be better. Yeah, there we go. Maybe, I don't know. That right there is 345. So basically, you have this space in between the pink and the black that you're basically trying to figure out what that angle is. So you just subtract the two, and then that's how you get 35 degrees. This. Okay. So I have a handout with all of this. These are basically the different types of polar coordinate equations that you can have. And when you graph these, they actually create different types of shapes, which are actually kind of fun and cool to look at, okay? And so with these particular ones, I'm not expecting you to be able to graph these by hand. I mean, now granted, you could, you can plug in any value in your unit circle, n for theta, find the sine and cosine of it, and then, be able to plot it that way. But I'm not going to ask you to do that. I mean, we're not spending like a whole month on polar coordinates, okay? So I do expect you to know how to graph these by hand. By using the calculator. I am also expecting you to be able to recognize which ones are circles, which ones are carnoids, okay? And so on and so forth. So, and I'm also expecting you to know what type of symmetry these have, okay? So let's go through each one, okay? You will need your calculator, so kind of go ahead and have it out. The first type you can have is a circle. And they're set up in this format, where you have R equals A sine theta or R equals A cosine theta. Now, what do you think A stands for? Now, R, it's an integer, like 2 or -4, so on and so forth. But it's basically a number that's going to either make this a bigger circle or a smaller circle. And one thing, so it's either going to look like this, what you have here. Now, if it's a graph that has a sine in it, it's going to be symmetric about that vertical axis. So in this example that I have here, this is an example of a sine polar equation in this format. The ones that have the polar axis, also known as your horizontal axis, as your line of symmetry, those are your equations when you have cosine. Okay? And so go ahead and pull up your calculator. We're going to go one by one, so you're going to see a picture of all these. We're going to graph R equals negative cosine theta. That's the first one that we're going to graph. Now, yes, it is going to look like a circle. So what you'll need to do is, if you have your own personal calculator, you might have to go ahead and change this. If you use one of mine, it's probably already been changed. But since we're dealing with polar graphs and polar equations, you need to make sure that your calculator is in polar form. So go to mode, go down and make sure that POL, it might be POL on some of you guys' calculators or polar in some, make sure that is highlighted. So go over, click enter on pole or polar so you can be in polar mode. Okay? And make sure it's highlighted, so make sure you click enter. And you'll know that you'll be in polar form because when you go to y equals, normally when we go to y equals, what do we see? Y1, Y2, so on and so forth. Well, in polar form, you'll see R1 and R2, okay? That's because all of these equations are R equals something, okay? So we're going to graph negative cosine theta. And theta is located where the x normally is located. So if you press that button right beside the alpha button, now you actually get a theta. Not an x, but a theta, because we're in polar form. Okay? Close it off. And before you click graph, some of you all have already clicked graph. Depending on who had the calculator before you, or depending on what you did on your own personal calculator beforehand, go ahead and press zoom, and then go to option 6. So zoom, option 6. because it basically takes you back out to a standard window. And then you can adjust as you need to, okay? So if you did zoom 6, did you get something that looked like this? Anybody not get anything that looked like this? Zoom in. Press zoom, go to option 2, and click enter. Okay? Now isn't this a circle? I know it kind of looks maybe more like an oval, but circle, yeah? And isn't it symmetric about your polar axis? That's because it was a cosine. Remember, it was negative cosine. So cosines are symmetric about that horizontal polar axis. Okay? There you go. Nice and simple, right? Let's go back to y equals. And lesson R2, let's graph sine theta, just so you guys can see the difference. Okay? Just so you guys can actually see the difference. So go and put sine theta, and then click graph. You see the difference between the two circles? I know it's probably not easy to see on mine because mine's colored. But one is symmetric about the polar axis, the red, which is sine, is symmetric about the vertical axis. We okay? So you'll always know that you're dealing with a circle if it's in that format. A cosine theta. A sine theta. Okay? And I do want you guys to be able to recognize this depending on what type of equation that you have. So we're good with circles? Mm-hmm. Cool. And I am going to ask you to graph these on paper. So I'm just expecting, when you graph, like say I want you to graph the blue one, then I expect you to, start at your origin, draw a circle as you go to unit 1, and then back, okay? It shouldn't be nothing that takes up the entire picture. Does everybody follow me what I'm saying? Okay. Yes?
Did you get alternative graph like if you use R1 and R2?
Yes.
Okay.
Mm-hmm. So I have both of them in there. All right? Now let's look at the next type, which is your carnoids, okay? Now carnoids, if you look at the general setup, is R equals A sine theta plus or minus A, or A cosine theta plus or minus A. If these are both the same variable, what do you think that means numerically? No, I mean, if you have A on the front side and A on the back side, then that means what's special about these numbers? Don't think too hard. They're the same number. Yes. So you are going to have like R equals sine theta plus 1 or R equals 2 cosine theta minus 2. Like they're going to be the same. And that's how you know that you're dealing with a carnoid. Okay? And it kind of looks like, well, one of my students described the other period as a petal. Like a flower petal.
Oh, like the pink scarf.
Yeah.
Heart.
Yeah, it's like a pad, like a lily pad, something like that. So we're going to actually graph this one. We're going to graph the top one, sine theta plus 1. So let's go back to our graph, sine theta plus 1. Now, is this going to have polar axis symmetry or vertical axis symmetry? Vertical. Why? Because it's sine. And when I graph it, there I go. Vertical axis symmetry. And if you had to graph this on your paper, you'll just start at the origin and you'll just make a nice little petal. I'm not looking for something that's like exactly perfect, but I'm also not looking for a petal that covers your entire grid because it doesn't. Okay? So far, are we okay? All right. Let's look at the next one, the limacons. Now, you got to be careful. Limacons are kind of in the similar setup as the carnoids. The only difference is that these numbers, they should be different. Okay? They should be different. So an example of that would be 3, R equals 3 sine theta minus 2. And before we go back to our calculator, if A is greater than B, then it's going to have a loop in it. Okay? If it's the other way around, if A is less than B, then it's actually going to look very similar to a carnoid, and the only way that you'll know which one it is based off of the equation. Okay? So if these values are different and A is less than B, so something like this, if A is less than B, then you know it's going to be a limacon, but it's going to look very close to a cardioid. Okay? So we're going to graph that top one. 3 sine theta minus 2. Make sure you close off the parenthesis on the theta. What type of symmetry should it have? Vertical. Can't see my full picture, can I? So let's go back to our standard window, okay? Press zoom and go to option 6 so you can see the whole picture. So far so good on the one so far? All right, I'm just trying to show you, what like the difference between the equation and what the graph looks like. I'm expecting you to be able to do this in your calculator and recognize which one is which, okay? Let's go down here to the spiral of Archimedes. Now this picture should look very familiar. Where have you seen this before, outside of math class? Conch shells?
Galaxy.
Galaxies, shells in nature, the whole design thing Ms. Dunstan was talking about. You remember when y'all watched that video in Warren Meeting? That spiral right here, okay? That is created when you have r equals n theta. N could be any value such as 3 theta. It's going to create a spiral, okay? So now you go back and you tell Ms. Dunstan, hey, we doing a design in our math class. She's probably so excited, okay? So we're going to do 3 theta, all right? And we are going to graph this. Looks like I might need to zoom out a little bit, right? Okay? Let's go zoom. I'm going to go to option 3 and zoom out so I can see the full spiral. The full spiral. Okay, so there you go. You have your spirals. Now we have 2 more to look at. We have our limit skates, which kind of look like the infinity, and then we have our rose curves. Okay. Now with this first one, you see we have r squared. So every single one is going to be set up as r squared, and then our equation. So you might get something like this that you have to graph. But if you remember, when you click y equals, it's only r equals. Okay? So how can I get r by itself without the square? Square root, both sides. And remember, when you square root both sides of the equation, you get what? Plus or minus. And so what you'll have to do is, because there's not a plus or minus button in your calculator, you're going to have to type in 2 equations to graph these, okay? You have to type in the positive square root of 16 2 theta in R1, and then in R2 you have to type in the negative version. So these will be the 2 that you would graph, okay? Now, you got to be very careful, because the one thing about it is the reason why you need both of them is because only one won't give you a full, complete curve. You need both pieces to connect them together. And since mine is color, you'll be able to see it really clearly what I'm talking about, okay? So we're graphing these 2 into R1 and R2. I'm going to go back up here, clear this out. Square root of 16 sine 2 theta. It was 2 theta, right? And then a negative, not a minus, a negative, you will run into an error message, 16 sine 2 theta. And look at mine. The first curve will be blue. The second curve will be red. Okay? And I'm going to go back to standard form. So if you take a look, there's the blue. You see how it doesn't complete, but then the red completes it? That's why you need both parts. Okay? I mean, on mine it does it really fast, so like if you blink, you've missed it all. Okay? So, there you go. You have your escape ones, okay? Not too bad, right? Honestly, I just need you to be able to recognize. This one is the infinity symbol. Cardinoids are the ones that look like a petal. Limacons have the loop. Of course, you got your circles. Your last type, your spirals. Don't forget about your spirals. And the last ones are your roses. Now, people really like the roses because they're the pretty ones, okay? Because they look like your old school flowers that you used to draw when you were bored and like back in elementary school, or maybe still now. I don't know. But they're set up in this format of R equals A sine B, or R equals cosine B theta. I'm sorry, I took the other one wrong. So let's graph this first one. 4 cosine. Let's go 3 theta first. Now the one thing that you'll have to notice too is that if B is odd, then you're going to have exactly that many petals. So you're going to have exactly that many loops. You're going to have 3 loops. But if it's even, your loops are doubled. Your petals are doubled. So let's graph this. I'm going to clear out all my other ones because I don't want that to throw me off. And because I want it to look pretty, I'm going to do it in the pink one. So we're going to do 4, what did I say, sine or cosine? Cosine 3 theta. Close it off. And when I graph it, you got 3 petals. Isn't that pretty? I know. So pretty. And if you notice, each petal goes out 4 units. Okay? So what you graph? You graph
Yes,
4 theta. So there you go. You got your petals. Now what if I change my 3 to a, let's change it to 8. How many petals am I going to have? 16. Let's take a look at what it looks like. Isn't that pretty? So, there's beauty in everything. Okay, but yes, these are your roses. If you have an even number for your B, that's how many petals you'll have. Okay? And again, I'm not expecting you to be able to graph these by hand. I do expect you kind of like to give me a quick sketch of what it looks like on paper, and then tell me what type it is, or even possibly the type of symmetry, okay? So are there any questions about your different types of polar equations that you can have, your more complex ones? Yes.
Don't leave it in radian if you do it.
Huh?
If you do it, don't leave it in radian.
Yeah, don't leave it in radian.
Let me just go ahead and show you some radian action. It's great.